Hi, Joyce. CalcBC. October 27, 2016.
See, that's why I thought, because I have to space on one but not the other.
Captain's log.
Okay, as you guys are trying, you already have it written down. Let me fill in Joyce real quick. Cool. Joyce, at the beginning of class, we went ahead and started with this multiple choice question. So why don't you pause? You don't necessarily have to do it in your spiral. It's kind of just thinking through. I don't want to make you write the slope field. But think through this one just for a little bit. I actually have the solution on the next page. You're just not going to hear totally all of our working out of it, but I think you'll be okay. So pause and just try to get an answer for this one. Okay, as you come back, we got it down to E because we were thinking about following the flow. The antiderivatives follow the flow. The little baby tangents themselves focus on the values of the differential equation. So then we saw the flow was logarithmic. The other ones wouldn't make sense. It's definitely not parabolic. It's definitely not exponential. Could be exponential with a vertical flip, but not letter C, which has a horizontal flip. And it's not trigonometric because it's not that periodic sinusoidal curve. Then we went ahead and tried one other one. So why don't you go ahead and ponder this one. So why don't you pause it just for a little bit and think through how to match this new slope field to its differential equation. Remember, think about the slopes, not necessarily the flow. And then as you come on back, we went ahead and were able to realize George was talking through, like, hey, let's look at where x is negative, which is on the left of the y-axis. We realized that all of the slopes on the left of the y-axis were negative, which means that x seemed to determine the sign because all the slopes on the right were positive. So then we're like, oh, hey, y's sign can't be a factor, so he must be squared. X's sign has to be a factor, so therefore he can't be squared. And to be honest, that kind of eliminated A, B, C, and D, and I just quickly pointed out the horizontal tangents are when x equals 0, the vertical tangents are when y equals 0, but then George was like, oh yeah, all of them have that, so I was just kind of trying to remind them of other clues to look at. So, final answer E. Now they're back in their notes. The example we left off yesterday, which was this one. And we're picking up, they were trying to get me little baby tangents at the different points. All right, guys. What are we going to do? What points are we plugging in?
1, 1, 1, 2, 1, 3.
Yeah, you can do 1, 1, 1, 2. Now this is going to get tedious after a while, right? So, Gerardo, it's not that you literally have to make a table for every single point. If the AP asks, guys, it's what, like 8 points, 9 points? So then we usually do a table for that so they can see our rationale and everything's clear. But this one, there technically is 9 points as well. Just to do it quickly though, if you notice, isn't it solely it being the differential equation because dy dx is y prime? Isn't it solely dependent on just the x's anyway? Mm-hmm. So when you plug in 1, 1, 1, 2, 1, 3, you're still just plugging in x is 1, and what is the value for the slope of all of those? 1/3 minus 1/2. 2, 6 minus 3, 6. Negative 1, 6. So you can go down 1 over 6, it's going to be very close to 0. Down 1 over 6, and we're just approximating, Charlie. It's not necessarily a perfect science, but you have to make sure if it's a negative number that anyone looking at it would say it sloped down.
But they're not all negative. Well, they're all negative.
Just be careful.
Yeah.
Because the AP guys are pretty forgiving as long as they can tell not very steep, pretty steep, definitely flat for a 0, definitely up and down for an undefined negative positive. That's all they care about. So you just have to be as precise as you need, which isn't that big of a stress as long as you're spot on. We have 2, 1, 2, 2, 2, 3, but all of them are just dependent on 2, right? So 4/3 minus 1. Uh-oh, wait, hold on. I think it's positive 1/3, right? 4/3 minus 1.
4/3
Oh, there you go.
minus
So that'd be 1/3.
1/3.
So it's going to go up 1. Yeah, up 1, 1, 2, and 3-ish. So it's not very up, but it is a little bit up. And then 3, 1, 3, 2, 3, 3, all dependent on 3 again. 3 squared is 9, 9/3 is 3. 3 minus 3 halves, 3 minus 1 1/2 is 1 1/2, right? So that'd be 1.5 or 3 has to be easier for rise of the line. We do up
You go down 3 and then over to the left.
Yeah, we could do that.
Oh, I started from the top. Okay.
Oh, no, that's a good idea. 1, 2, 3, and over 2. So we can read the size. So then, technically, if you think about it, we can fill in these pretty quickly. The only thing we didn't fill in was when x is 0, but when x is 0, what's that one?
I'm trying to
Yeah. Just make sure they look flat.
when we have y equaling 0, would they be closer to 0 or no? No, they wouldn't.
I didn't even follow. I was trying to figure out what it was.
Is this kind of like a form of anti-differentiation?
It's not a form, but remember it is showing the flow of what the anti-derivatives are supposed to result in. So it's kind of like a, not experimental totally, we're literally looking into finding those baby tangents. So it is an actual, but it's more of an exploratory way of trying to figure out the behavior of the antiderivative without actually using integration.
You probably won't be doing that part of finding slope fields unless they ask you to find the slope field. They really do that. The only other time is like when they give you a graph and trying to find it, but you won't really be using integration to try to find the real slope field.
Cool.
Integration, what am I talking about?
Going backwards.
Finding an antiderivative, right? So going backwards, I need to see my y prime as a dy dx, as I already stated. Do you remember from yesterday or from the past how we orient everything to be able to start integrating legally?
Multiply dx.
Multiply dx. So we move dx to the other side. Remember, we have to sandwich it, and then we're allowed to go. We have to separate the variables, separation of variables. And you guys go and I go. Sound good? We'll collaborate. Remember, do we need plus c's on both sides? Nah. Plus c1 on one side, plus c2 on the other would be a new plus c3 on the original. We can do this thing. So does it kind of make sense in the graph that we have this would be a cubic? I think so. That has some sort of,
Little cubic looking 0.
yeah, so if it had 1, 1, it's going to somehow have some sort of maximum here, so I'm assuming it's going up, and we don't totally see all that. It looks like there has to be a minimum in between if it's continuous, right? Go from negative slope to positive slope, something cubic. Sounds good. Cool? Let's keep going. We already did him. So what about him? Okay, not bad though. Do we have to make a table really? What can we say right away everywhere where x is 0?
Where x is 0 is 0.
Except for, what's the one point I have to exclude?
0, 0.
Yeah, 0, 0, he's,
The vertical.
yeah,
Oh, well, actually.
we leave them blank. Because that's the struggle, right? 0 over 0. So, leave them blank, but we'll make these horizontal. What are we going to do for y equals 0?
Or vertical.
Yeah. Vertical tangent.
And then,
It's okay, should see me
Whenever-
grade 1 today. 5 minus 1 is 5, all sorts of weirdness.
so then the first quadrant they're going to be negative.
Mm-hmm.
The second quadrant they're going to be positive.
negative again, so negative, negative, negative.
And then fourth quadrant.
So then at 1, 1, that one's easy, so it'd just be -2. So down to right 1-ish. At 1, 2, that would just be -1. So up 1 over 1-ish. So you see a little bit less negative. -1, -2.
Positive.
Oh, sorry, -1, -1. My bad. That's +2, right?
Yeah.
Up 2 over 1. And then -1.
Wait, no, it would be negative, wouldn't it? Oh, because it's a positive line number.
Oh, I said it wrong, didn't I?
No, I saw it wrong.
I think I might have said negative. Sorry, -1
A
positive.
little less positive.
A little bit less, right? Like up 1 over 1.
Maybe positive 2. Oh,
-1.
I don't know, this is.
That'd be 2, and then 1, 2, that would be 1. Yeah, positive 1.
I'm just trying to catch up here.
Probably something elliptical, yeah.
Oh, yeah.
And then -1, -1, that's gonna be a negative again, and a -2. So down to 1. And then a little bit less negative. And then positive, less positive, more positive. Protein. But anyway, we know what we're doing, right?
Yeah, now, but I don't want to do it anyways.
Well, now you do. Oh, sorry, I didn't fill in. There is no 7-1A, so let's just get rid of this slide because I just did 7-1A to be its separate section, so we can make 1B. Euler's method. Looks like Euler, but he's not.
Since this is the same section, do we put it inside?
I like it separated just because then slope fields is his own dude, Euler's is his own dude, because when people go back to review, some people will remember slope fields more easily than Euler's, and it might be nicer to have another patient. So that's all.
These mathematicians, they're all Pythagoras. Can you just do one thing and like be done with it? Pythagoras is way more than just a theorem.
Yeah, we got that perfect. She's asking why would you want to stop?
Because
You're
Euler,
saying why couldn't you do
he
way
made
more?
a number, he made a bunch of logarithmic. I'm like, he's gotta have a method. What is
So
this?
why wouldn't you want to?
Someone else can do it.
He wants to spread the love, spread the intelligence.
If somebody else could come
Hey, you're a communist.
Did you just ask me if I'm a communist?
up. There's nothing better than communism. It's already Satanism.
Because communism is all for the common good, right?
Common good of the people who want
You
to
know,
be rich.
technically speaking, we've never had a true communist government ever.
My
Because-
dad, he's an institution. He always used to say, "What would be the perfect government? Like if we were perfect people, and if God was truly in charge, it would be communism."
Yeah. Only thing is that communism has so much negative connotations associated with it.
That's because we've never had a true communist.
So we're not perfect, and God's not been in charge.
He
I
used to be
mean,
in
he's
charge of
sovereign, but he hasn't been actively enforcing his rule in our daily lives. How about that?
It'd be kind of cool
That's
though.
what sounds fun.
Like in right before Kings, like they had God as their king, and they just like looked to God, and like this powerful voice spoke. But they're like, no, we want a king. It's
Yeah, see, it was supposed to be.
like,
Fire in the cloud, right?
yeah, but then they just wanted a king. It's like, how useless is that?
But come on, isn't that our own weakness? We turn much more quickly to things we can see than things we can't. That's how we
You
analyze
can't
things.
see a huge ball of fire, and
That's not, well, that was the thing. Everybody got to see it. You wouldn't just talking
oh
about
yeah, true.
So they didn't have what they felt to be a relationship. You know what I mean? Like in the Old Testament, it was hard. He did have relationships with people, but the common man mostly just needs to trust. What?
Oh, for reading that manifest.
We're watching a movie here in regular English.
Or
Yeah, I should take AP.
Numerical approximation of the particular solution. Numerical approximation. What? It's not a slope field anymore. So these are both approximations. Slope fields approximate. I mean, they do it specifically with tangent lines, but you get to approximate the movement, right? We're definitely approximating when we try to follow the flow. Hopefully pretty accurate approximating. So. This is numerical. Uh-oh. Numerical? Not graphical. approximation of a particular solution to the differential equation. So this is another way of going back to an antiderivative and trying to figure out some stuff about him. That passes through a given point. I put x of naught, y sub naught. You put x of 1, y sub 1, I suppose. But no, don't.
You want an initial point instead of.
Yeah.
Just why does that kind of look like, I don't know, like two variable differential calculus?
Because they're two variables. Slope. My differential equation finds the slope, right?
Yes.
Do I have anything to write for that? Not really. Okay, starting point. I mean, I could.
Such that x, y.
Yeah, I could do that.
That's why I love this class. We can actually interact with what notes we take.
Starting point. X sub naught, y sub naught. Steps. So if we have a slope and if we have a point, what have we done before that? Given a slope and given a point, we can actually make?
We can make a definite.
line.
You can make a definite integral into an integer.
Not with specifically what I was saying, a slope and a point.
Oh.
Like a slope, like a specific slope. So theoretically, we could go ahead and put this even as, just to get the ball rolling, a specific slope at x sub naught, y sub naught. So we're given an n, and we're given a point. So we could go ahead and we could plug in y minus y sub naught equals n times x minus x sub naught, right? But look at what we're trying to do. Aren't we trying to approximate the f value? So what if we were to rearrange a tangent line? And what if we were just to get the y by itself? Move the y sub naught to the other side. Question. Would this perfectly work? Would, when I plug in x sub naught, y sub naught, and the n?
I'm sorry, it's funny. That actually looks like the physics equation.
If I plug in x sub naught and y sub naught, and then if I plug in x sub naught again, am I going to get y sub naught?
Wait, what? What? That's y.
If I plug in, just real quick, I'm asking if this would precisely work at the beginning point. What if I was to plug in x sub naught? Would I get y sub naught?
You would get y equals x naught.
Yeah, because this is 0.
That's just 0. That's perfect, right? Now, you're like, well, that's pointless. Why would we ever use that equation to find y sub naught? Oh, we're not going to. But we're going to use it to approximate future y's. Isn't that tangent line approximation? Kind of.
Like equation and that stuff.
We're going to start with an initial tangent line. We're going to start with an initial tangent line. An initial tangent line at an initial point. And we're going to use tangent lines to get to future points instead of using integrals. Because we kind of did that last chapter in the sense that, remember, we could start with an initial point, a differential equation, but then we had to use our calculators in order to go and find future points of the antiderivative. Okay. Now, real quick. We're going to move away. We're going to start at y sub naught, which is going to equal f of x sub naught. And then we're going to move slightly away from that by a certain given step. We're going to be given some sort of step size, and the step size is going to be seen as our delta x. Now, sometimes they give it to us, and sometimes they give us a clue, and we have to determine the step size. They say, take 2 steps from this number to that number. Okay, I'm going to have to go by halves, or ones, or fives, etc. Take 3 steps. Okay, I'm going to have to divide that. So we might be kind of using our dividing into equal subintervals sort of idea. But then we're going to move to another y. And as we move to another y, actually, can I rearrange this real quick? I'm going to do f of x sub naught equals y sub naught equals, etc. But then we're going to move away, and we're going to say f of x sub naught plus delta x equals y sub 1, which is approximated by. As soon as we move off our tangent line, and we're still using our tangent line, now it's approximate. But you're going to see in just a second why this can be a good approximation. Because before, it's like if you only used one tangent line, well, as soon as you get away from your point of tangency, it's not going to be so hot, like as soon as you take a few extra steps. And then we don't have to take one step. For instance, this could be the f of x sub 1, which is y sub 1, which is approximated by. We could go again and we could say, hey, let's move away by the same step and let's get an f of x sub 2, which is going to equal a y sub 2, which is going to be approximated by. No, what are we approximating it by? Well, let's go figure that out, okay? Do we have it so far so good? We've gotten the idea of we start with what we do know. We start with an initial tangent line. Somehow we're moving away from that, but in a way that's more efficient than just moving on the tangent line. Oh, well, Here. Yeah, one little step. Here's the idea, we're not going to use the tangent line to help us with the first point that's given to us. We're going to use the tangent line to help us get to a second point. But we're not going to keep moving out further on that one single solitary tangent line. We're going to change the tangent line to be better. And then use another tangent line to separate for the second step. And another tangent line to approximate for the third step. And you're like, wait, how can you be using lots of different tangent lines? Can you guys tell how they're different tangent lines? What changes in the tangent lines? Well, the y's change, right? We start using the y we know, then we start using the last y approximated that we found, then we're using the last y. So we're changing the y's every time. What else are we changing? Not the step, that stays the same. X step can be H, X step can also be, if you want to put it in parentheses, but we also show that it's delta X. The step is the same every time, but we're getting farther and farther away. But who is this? Wait a minute, no, tangent line, that's supposed to be an M.
That's the slope.
That's the slope as found by plugging a point into who? The differential equation. So we're plugging into a differential equation and we're getting a new slope every time. So we're not just sticking with one tangent line with one slope that was good at one point. We're going to use him for just a little bit, then we're going to go ahead and say, oop, reevaluate, let's try another slope. Use him. Oh, reevaluate, use another slope. Use him. So we're reevaluating as we go step by step by step. And we can go until, well, basically until we get to whatever x they're asking for us to approximate the y at. So we don't need the tangent line for the first point. That was kind of silly. Like, we already have him, but we're going to use a tangent line to get the second, use another tangent line to get to the third. But I think this really doesn't start to make sense unless we look at a graph. Please, do I have another graph on the next page? Yes. I thought I did, but I couldn't remember. Okay. Where's your x in that, y in that? If I were you, I would pause and orient first. Where's our f? Right here.
Oh, I see what this is.
Right? Here's our f. Okay. Where's our x in that, y in that? Where the initial tangent line is. Okay, I don't need any help getting y in that. I'm good. It's the point of tangency, no big deal. But I'm going to use the first tangent line, and I'm going to take whatever step they tell me, And I'm going to get a new approximate of a y.
Isn't that like really fun?
Well, it depends on how zoomed in you are. But like theoretically, some of these will be 0.1, 0.01, so it's not really going too far. Then it's like, reevaluate, that was great and all, but I need to get way over here, so I don't want to use this tangent line. He's going to get worse and worse as he goes. I'm going to use now and say, hey, who's your slope, buddy? Oh, hey, your slope is that? I'm going to use that slope. Pick a parallel tangent line. So I'm going to use the new slope at x1, y1, and a new tangent line to get to a new point, y2.
Can h be different numbers?
No, it'll be
Constant?
It'll be a constant step size. And then I can keep on going. What am I doing? I'm trying to, using tangent lines, skim the graph as best I can. And the smaller the step, the more it's going to skim. Does that kind of make sense? Okay, so how does this all play together? You could write down what this is. Basically, the graph is the most important point because all of that is, well, basically what you just wrote. But we're moving along a tangent line, and then we're reorienting and saying, hey, let's get better. Hey, let's get better. Hey. Because otherwise, as we know, the error is going to get pretty big. So, ready? Now, George, this one, it's a big step size, right? The step size is 1. How accurate is that? We're just trying to start with an easy step size. Does that make sense? Okay. We're going to get to y is 4. So at the end of the day, what we're really hoping to have, y of 4 is approximate. Okay? At the end of the day, y of 4 is approximate, but we have to take steps to get there. Where are we going to start at?
0, 1.
Just to get us set up, if we're going by steps of 1, who's going to be next?
2. Well, 1.
And then y of 2, and then y of 3, and then we'll reach our y of 4, right? Now,
They don't give us a function.
no, but they did give us
Oh, y for every time. What time?
a differential equation. Yeah. So we could rearrange this if it helps. We could go ahead and make it y prime equals 1. You can't always rearrange it, so you kind of have to be careful, but this one you can. So y prime equals y, so dy dx equals y. Okay? Now, do we need any help getting y of 0?
No.
No. Easy. Okay, do we need help getting the next one? How are we going to get help? Think about it. y1 minus y sub 0 equals, I could plug y of 1 into the tangent line from him. So we can say y of 1 is approximately, think tangent line approximation. Who would be my other y value? Y of 0. Plus,
Plus f of
which is like my m. So where are we going to get my m from?
the y after.
Uh-huh. And I'm going to write it as the differential equation. You get m's from the differential equation. And what's the point I'm plugging into the differential equation? Just to help us
0, 0, 1.
0, 1, right? X is 0, y is 1. But it's m times delta x.
Which is
Delta x is my step, and my step is 1. So then all we have to do is solve.
so 1 plus,
So then plug in. Now why can I put an equals here?
because we are for sure that's, because it's our initial.
Because all of this is approximating to. Does that make sense? I put the approximate once, so all the work I have over here is the approximation for. Is that cool? So then, who's y of 0? 1. Plus, plug in 0, 1 to my differential equation. Well, just plug in 1, right? Okay, plus 1 times 1. Equals.
Why do you plug in just 1?
Oh, because there's no x to plug 0 into. Some differential equations have an x and a y, this one just has a y.
So it's 1, why is it 1 times 1?
Oh, because my step size, my delta x,
Yeah.
is 1. So 1 came from that, and then the other 1 came from this. Sorry, does that help if I did like that?
Yeah.
Now, we're at a new point all of a sudden. We're at 1, 2, which isn't on the curve. Remember, we're just kind of like on that, like, ooh, we went out a little bit of tangent line. Oh, reevaluate. So now to get to the next one, we're going to say, okay, let's use the last one that we had.
So y of 1 plus f of 2, 2.
Who's my x? My step size still 1. Are we okay? And then who was y of 1? My approximate? 2. Plus f of 1, 2. I'm just plugging in the 2, right? Okay.
Where are you getting the point?
Say it one more time.
Where are you getting the point of that?
Oh, remember, to get to a new point, I have to use the previous point. So I'm not going back to the original. Yeah, so x was 1, y was 2.
How did you know you used f of 0 comma?
Because that was my initial condition that they gave me.
And that means plug in 0 and 1
X is
into
0, y is 1. Plug in whatever you can.
the.
Because if the differential equation was x plus y, we would plug in both.
So just plug in 1 into the y.
And the next one, just plug in the 2 into the y. That's all I have.
So that gives you y prime.
Which is your slope. So then I can go ahead and say y3. Do you guys get the pattern? y2 plus, who did you put it in? What point are you putting in? 2, 4. y2, our approximation was 4 plus just 4, right? Equals 8. So at the end of the day, my approximation for y of 4 is 16. Now, to prove a quick point, if I was just to do linearization, aka just use a single tangent line, the initial tangent line at 0, 1, to estimate 4, which we know is a bad idea. That's 4 away. There's no way that's close, right? It's not usually. We would have done y minus 1 equals y prime, which would have been 1. It was just our initial. X minus 0. We would have plugged in and said, hey, what's going on when x equals 4? Y equals 1 plus
4 plus 1.
You see how they're a little bit different? This one keeps on following the curve to get up to 16. This one says, I can only get so high. Which one is a better approximation? Not him. We've used him to approximate for very small step sizes. This one can even be more precise for larger. How would you know for sure?
Plug it in.
You have to integrate. Right? dy dx and then so forth. We'll see tomorrow. Kiddos, in your homework for Southern 1, there are literally, and this is because I could only find, I think there's like 2 or 3 Euler's method only. So, I would say do all of your homework up to the Euler's method. If you can attack one, attack one. If you don't attack them all, let's come back to the second. Alright, bye guys. Someone better wake up soon.
Sam!
Video games.
I want to do that. Joyce, wait. Joyce, if you enjoyed this video, like, subscribe, leave a comment in the description below.